Hi, welcome to the second workshop of Chem 6161. We will start with the first question. The first question basically is draw the final product and justify which reaction will give better enantioselectivity based on the mechanisms. Okay, we have this compound. Remember that I changed the phenyl for a methyl. Okay, and we have these two reactions. Okay, how we can know which reaction will give better enantioselectivity? Basically, we have to analyze the transition state and, in the best approach possible, see which of these two compounds presents less problems. For example, in this case, we are doing a cyclopropanation. That means that I will draw the transition state. Okay, I draw the copper. Okay, all of this is on the plane of the slide, of the whiteboard. Okay, this phenyl is going in your direction, this phenyl is going inside. And then what we draw is the carbene. We insert the carbene. Now remember, we can do it as we wish. What I put is the carbene is perpendicular to the whiteboard, and I put the ester going in your direction, in front of the slide, and the hydrogen inside. If you do the opposite, you will get the same result. Okay? Then, what we know is that because this ester is up, the approach of the double bond has to be perpendicular to the carbene, but from behind. Okay, and but here, which side? Okay, the side will be if the alkene is approaching to the carbene perpendicular from behind, what it's doing is we have a hydrogen in this direction, isn't it? But if we come from this side, this alkene that is coming from behind the whiteboard is crashing with this phenyl. Right? That means that the approach has to be from behind and from this side. Then the substituent has to be as far away of the bisoxazolene. That means that has to be like this. I'm pointing down, that is where we have less sterical interactions. Okay, and now we do the approach for both substituents. Okay? If we do for this substituent, this is the ideal situation. We only have one substituent that we can put it down and from behind. Okay? That means that this will do the cyclopropanation, and what we will get is this final compound. Okay? However, when we analyze this case, what is the problem? Well, the phenyl, we can put it in the right position, but the methyl will always crash with the ester, with the phenyl. That means that this will destabilize this transition state, and for this reason, we will get low enantioselectivity. Okay, we destabilize the transition state, the stereoselectivity will go down. If we draw the cyclopropanation, what we will get is the main product will be okay. That That means, in this case, the transition state will be destabilized because this methyl is crashing with this phenyl with this ester. Okay? Good. Go for the number 2. The number 2 is very similar, but now we are analyzing Jacobsen epoxidation. Okay, for the Jacobsen epoxidation, we have these two compounds. The cis and the trans. Well, what we can do is first draw the transition state. The transition state of the Jacobsen epoxidation, remember that it's something like this. And then we have all the carbotyls. Okay, the manganese is planar, and all these substituents, the 2 nitrogens and the 2 oxygens, are perpendicular to the whiteboard. Okay? That means we analyze how we can approach this oxygen. Well, we can approach from this side, but what happens if we approach the alkene from this side? It's crashing with these 2 terbutyls. The second option is that it's going from behind, okay, but then it's crashing with this terbutyl. Or the approach can be from in front of the slide, but then it's crashing with this terbutyl. That means that the only option is that the approach has to be from this side. When we consider the approach of this side, the only that we have to be careful is with this hydrogen. Okay? That means the approach has to be with the double bond in this way to the oxygen, but with the bulky substituents far away of the cran-cycloxyldiamine. That means the bulky substituents going up. If we have here a metal, the metal has to come in this direction. This has to be the approach. If this is the double bond, this is the pencil is a metal, has to be up in order to avoid that it's crashing with the cran-cycloxyldiamine. And if we have 2 substituents, the minor substituent has to be over the hydrogen. That means if we only have a methyl, the approach will be like this, with the hydrogen over the other hydrogen, in order to avoid steric interaction. Okay? Well, then, if we approach this, okay, the approach will be like this. Okay? We have the 2 big substituents up, and the methyl over the hydrogen. That means that this transition state is favorable. Okay, if we do the epoxidation, what we get is this compound. Okay? But what happens if we approach this compound? Okay, if we approach this compound, the bigger substituent is the phenyl. That means that we need to put the phenyl in this direction. But if we put the phenyl up, always the methyl will go down. That means that this methyl will crash with all the cran-cycloxyldiamine, destabilizing transition state, and anti-selectivity will go down. Okay, why? Because simply there is no good approach. That means that all the approaches to this transition state will be with high energy. That means will be less differentiation between the possible approach. That means lower E. If we do exactly the same, what we will get is this final compound, this final epoxide. Okay? Again, how we do this type of exercise? We have to check in which of the two approaches we have less problems. Okay? And then we can determine which will be the approach with more energy. That means that we'll have more problems, and the approach that has more energy, more problems, means lower E, or lower stereoselectivity. Okay? The last one, we are working in a laboratory and we only have these chemicals. We have this ketone, we have titanium isopropoxide, we have this, the oxidant, we have sodium borohydride, we have minus diethyl tartrate, and we have this compound, and we have BH3. And the question is that we need to synthesize this compound and this compound A and B in his enantiopure form. How we can do it? Well, the first thing that we can do is we have this static material that basically is the final product oxidized. That means that if we reduce this alcohol, we will get one of the two. How we can reduce? We can use the Korey-Bach-Shibata method. Okay, remember how is working the Korey-Bach-Shibata? We have this compound. We make the bisoxazolidine. Okay, and then a second unit of boron is added here. We know that the ketone is coordinating with the boron because one orbital is empty. Okay, and then if this is going up, we have to put the bigger substituent going down and the small substituent going up. And then what is happening is that one of these hydrogens is transferred to the ketone by the phase that is inside of the slide. Okay? This is how it's working. Yeah? Okay, then we know that this is the large substituent and this is the small. That means that if we do this, basically what we will have is this compound. If we do the reduction, what we will get this compound B. Okay? Easy. That means we reduce this compound with the Korey-Bach-Shibata, with the catalyst that we have in our lab, and we get the final compound. Now, how come we get the other one? Okay? The other one is more difficult because obviously should be easy if we have the enantiomer of the catalyst, but we don't have it. We only have this catalyst. Well, one of the options is to remember that the Sharpless epoxidation is not only good to do epoxide, but also to do kinetic resolutions. That means we have this compound and we reduce with sodium borohydride. What we get is a mixture of the two possible enantiomers. Okay, we have 50-50, it's alkyl. And now what we can do is a kinetic resolution in order to resolve this mixture of enantiomers. Okay, remember how we do it? We put the alcohol in this way, and then the only that we need is to draw it in this way. This is this enantiomer. For this enantiomer will be exactly the same, but with the metal going down. And then we know, we check the mnemotechnic rule, that the minus diethyl tartrate is attacking from up the upper phase. I mean, it's attacking from this phase. What is happening? In this case, the approach of the epoxidation is okay because we only have a hydrogen here. That means that will work normal. However, in this case, when the epoxidation is approaching from this phase, what is happening is that it's crashing with the metal. If it's crashing with the metal, the reaction will be slower. And with a little bit of luck, will not work. That means we do the epoxidation with minus diethyl tartrate, the oxidant, and what we'll get is this compound that will not react because when it's doing the epoxidation it's crashing with the metal, plus the epoxide. And this is how we can synthesize this enantiomer. Okay? It is clear? That means we play with the two options. One is the direct reduction of this compound by a chiral means, by Koenig-Shibata, and we get one enantiomer. In order to get the other, we reduce, we get the racemic, and then we resolve the racemic by a Sharpless epoxidation. Okay? Good? You know, if you have any questions or any doubt, feel free to send me an email. I will try to answer your questions. We can have a meeting, etc. Okay? See you soon.